Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into section 5.3 in the Big Ideas Math Integrated Math 3 textbook. We are going to be transforming exponential functions and logarithmic functions on graphs. So, or also describing them from a graph or from the equation or whatever it is. Now, we've seen this before, A, H, and K, and they are involved. Our translations, our stretches, our reflections. But we have to understand our parent functions. Now, exponential functions, I'm going to have some basic expectation that you have some understanding of how those things are graphed, or at least in the way that I teach it in a tableless format. I teased a little bit more of it in section 5.1 on those graphs, and in logarithmic functions, although we started doing it for the first time in section 5.2 with an inverse of the exponential functions. I won't do it off the inverse anymore, and I'm going to try and explain it from there as well. You want to think inverses of exponential functions though, or at least you want to think of how you calculate logarithms in that way. Now, if they're going to be using e and natural log, which I very much assume that they're going to be doing so because that came off of 5.1. We're going to have to use the calculator for some of those ones, or we're going to have to remember what some numbers are. Like e is around 2.7, e squared is around 7.4. I've stated those things before, so get ready to hear those again. We're going to start with the lecture portion. If you'd like to download this portion below, or this PDF below, you can find it in the description section. And you can also find the graph paper that I'm going to be using, probably the tall kind. I'm going to go tall for exponential functions and wide in the wide form for the logarithmic functions when we do them. Likely, that's probably the best way to go about it. And find the timestamps down below for certain things that you're going to want for problem set or the lecture portion. As I stated, I'm going to start right now, as well as the playlist for the whole IM3 set down below. We're going up to number 56 today. Without further ado, guys, we'll go ahead and get started once I hit my proper hotkey to move forward. We're going to learn to transform graphs of exponential and logarithmic functions, again using A, H, and K. Looks like straight off the bat we're going to talk about them, and write transformations of them. So all stuff kind of old, only we have to understand our parent functions and how I'm going to be graphing them. I'm going to kind of state them out loud as I do them. I think you're just going to learn off of that. Your teachers might say something different or something similar. They might sound different, but they represent the exact same thing, even or especially if they use a table. You can transform graphs of exponential and logarithmic functions in the same way you transformed graphs of functions in previous chapters. No change. Examples of transformations of the graph of f of x equals 4 to the x power are shown. Interesting. Normally they'd say 2 to the x as the parent function, but that's okay. Horizontal translations are x minus h's. They're things inside of the function itself. Now, your function is an exponential one. That means it's inside the exponent. So with this x minus 3 up there, we translate 3 units to the right. The way that I'm basically going to explain it is ask yourself what value of x gives you 0. And that's important because that's the value that you raise 4 to the power of to make 1, to make it unchanged, to make it multiply by your a value, which you don't see the a value right here. This would be 1. 1 times, if x is 3, 3 minus 3 is 0, 4 to the 0 is 1, and anything times that 1 is just that number, whether it's a, whether it's 1, whether it's a negative number, whatever it is. So that's why 3 is the important number that we, again, flip. And then x plus 2 is 2 units left, etc. I'm going to be starting from that point. I'm going to translate over, and I'm going to go a units up from the asymptote on that. Now, I'm actually going to start every single graph, though, with my horizontal asymptote. If you know exponential functions, have horizontal asymptotes, and if I do things in relation to it, I can translate up or down from there. Normally, we start by default at y equals 0, the x-axis, and if we go plus k plus 5, we go 5 units up. There's the asymptote 5 units up, or 1 unit down. There's my new horizontal asymptote. I'm going to start by graphing the asymptote each time plus k and go in relation to that. Now, reflections can be had inside or outside right here, and they are 2 different kinds of reflections. Flipping it with a negative x is flipping in the y-axis, and as you know, negative exponents means division, which is why it becomes decay. This is the same thing as 1 over 4 to the x power, like that. All right, so there's just a version, or how I should probably put that, 1/4 to the x power, if you will, because that's a version that says, hey, it's decay because b is a number that's between 0 and 1 as opposed to more than 1. Negative 4, what I want to remind you of with this thing here is that the negative is applying after you raise the exponent. This is actually negative 1 times 4 to the x power, which is a really important distinction because in a case like this, we need to note that 4 is still the growth rate. You can't have your b value be negative in an exponential function. It must be positive between 0 and 1 or greater than 1 to actually behave like that. So negative 1 in this case flips the graph over, makes like the y-intercepts negative or whatever you want to talk about, and then it goes from there. Now, horizontal stretches and shrinks are things that, you can work on if you want to. When it says 4 to the 2x power, that's also 4 squared to the x power, which is 16 to the x power. You can graph it like that. Or 4 to the x over 2 is 4 to the 1/2 to the x power, which is the square root of 4, which is 2 to the x power. You can change these graphs by nature if you so choose to, and just make it, instead of a horizontal stretch or shrink, you can make it a part of your growth factor. That's up to you. Either that or go based off of what we've seen before. Horizontal shrink is when the number gets bigger. Horizontal stretch is when it gets smaller. You just widen the gap on x's. And I'm fine using those. I just want to remind you of how you can use transformations with them on exponentials. But we got to talk about those with logarithms. Last set is vertical stretch and shrink. I probably should have talked about those before. This is when the a value changes, and this is the value that this is the first point, what I call my reference point, that I tend to start with after I'm translated by k and by h, and I'll go up a units from there. Because again, when x is 0 is when your y value becomes 3. When x is 0 is when your y value becomes 1/4, because anything to the 0 power is 1, and it basically goes away in the product. So then you're left with a on that. So I don't know, I kind of skimmed through this to see if they use tables. They do not, so I got to talk about the graphs that they have as a result, but that's just a good revisit of all our a, h, k, and where they exist. And there's b. b is your growth factor. That's 4 in this case. So how I'd be graphing these things here. Describe the transformation of y equals f of x. F of x equals 1/2 to the x power, represented by g of x equals 1/2 to the x minus 4. Now, for me personally, I can go straight off this and feel good with it. Obviously, I'm going to be graphing both of them. If you do have your parent function, what's happening from the parent function to this one? Minus 4 means it's translated down 4 units. So the original graph has a y, not a y-intercept, a horizontal asymptote on the x-axis on y equals 0. You can notice that it shifted down 4 units. That's how I would start my graph. I'd start with this thing down 4 units from there, and there's the asymptote. Now, what you'll also notice in this graph, the original f of x is, although there's a number missing, this would be a 1. Because x minus h is x minus 0, there's no horizontal translation. I'm going to actually start 1 unit up from the asymptote right there. That's how the 1's represented. The 1/2 will show how many times, what I multiply by. 1/2 each time, x increases by 1. Over 1 is times 1/2. Half of 1 is 1/2. Half of a half is a quarter. Half of a quarter is an eighth, etc. And I can divide by 1/2 going to the left, which is multiplying by 2. 1 times 2 is 2. 2 times 2 is 4. And I'll get those points. Now, g of x is the exact same, only it's translated 4 units down. But if I start from there, if I start with my asymptote and I go 1 unit up from the asymptote, because that's my a value right there, I can do the same things. Half of 1 is 1/2. Half of a half is a quarter. Notice I'm not doing it based off the y values. I'm doing it based off distance from asymptote. And an eighth up from the asymptote. And I can go divided by 1/2 is times 2. 2 up from the asymptote. 4 up from the asymptote. I can go 8 up from the asymptote just by doubling that way. So those are the kind of points that I'm going to plot. I always say plots that I'm going to point. Points that I'm going to plot on those ones. And this is indeed just a translation 4 units down on that. Translating a natural base exponential function. So yeah, we are going to be using e to the x. Now, they weren't too particular as far as showing what those points are, but let me kind of demonstrate them right now. From our basic e to the x graph, we have, once again, a 1 as this guy right here, our a value, which means we'll go 1 unit up from our asymptote at our translated point when it comes to h and k. There's no translation on h and k, so I'm going to go 1 unit up from here, and there's that point. Each time x increases by 1, I'm going to multiply by e. Over 1, up e, or not up e, but 2.7 from the asymptote is right there. E squared up from there is around 7.4. There's that other point. 1 divided by e is around 0.36. I think we've seen that. You might have seen that with me before. And then just makes it a little smaller, a little smaller. It's close to 1/3 of our numbers, and that's kind of how I round it. Again, they didn't use a table. They don't even show any points, so I'm going to do the same thing off that. Now, the translations here are x plus e to the x plus 3 power and plus 2. The x plus 3 right here means we're going to translate 3 units left. The plus 2 means we're going to translate 2 units up. So I actually start with the horizontal asymptote, translated 2 units up there. I'm going to be at my 1 a value when I'm translated 3 units over to the left, because when x is -3, my y value becomes 1 up from the asymptote right there. So that's my reference point. This is where I start. From there, it's times e, units up from the asymptote. That's 2.7-ish, and then 7.4-ish, etc. We plot those points and we go at it. Divide by e this way. So hopefully I'm giving you a good example of how I'm going to do my graphs from there. Obviously, I'm going to build it in the actual problem sets themselves. Transforming exponential functions in a second set. Here we're now going to be doing horizontal and vertical shrinks and stretches. So a horizontal shrink, this one's actually pretty interesting because it has the translation as well, and I got to speak on that a little bit. Note that generally, I'd probably have to factor out this. Okay, this is an interesting question. Normally I'd have to factor out this 3, but this is going to look a little weird as well, x minus 5/3. I bring this up because there's a certain value of x that gives me 0 for the exponent, and that's going to be 5/3, not 5, but 5/3 when I factor the 3 out. So when x is 5/3 is when I will be 1 up from the asymptote. So apparently on the red graph, I have to go over 5/3. Where am I? I'd have to go over 5/3. That's 1 2/3 to go up to 1. So that's that starting point for me, I suppose. That one's a little bit different than I'd normally do. Maybe I'd have to do some things with the table on that to make most sense of it. Like I can plug in 1 and 2 for x and get some other actual values. Maybe I can work it out better. But that's otherwise a reference point. Remember, reference point can be whatever you want. You can plug in any value for x, make it a reference point, and use your b from there times 3 times 3. So I'd probably do this one instead. But that explains why we go over 5/3 just to go up 1 instead of going over 5 to go up 1, right? The point's not right there, not at all. Anyway, there's also a horizontal shrink on this thing, and I guess that's the other thing I'm going to talk about. With this 3 here, it's a horizontal shrink by a factor of 1/3. So actually you have to go over 1/3 to go up 3 times bigger, and go over 1/3 to go up another 3 times bigger, I guess, to 9, and there would be a point right there. Now, the original f of x equation I probably should have started with, you go up 1 right here, and times 3 is you go over by 1, and times 3 again like that. So that's a basic one, divide by 3, divide by 3. Hopefully this lecture is making some sense. E to the negative x, you have to recall, is the opposite of e to the x in the sense that it's a reflection over the y-axis. It's a decay instead of a growth. So now you divide by e, because remember this is 1 over e to the x power, if you want to put it like that. You're dividing by e each time you increase x by 1. So even though you start at 1, you divide by e, which is close to 1/3 and close to 1/9, stuff like that. And here's your 2.7. So it's a decay instead. This one has negative 1/8 e to the negative x power. That's an example of reflecting over the x-axis. That means that the decay is reflected over here, and it goes like that. The 1/8, the negative 1/8 actually comes 1/8 down from the asymptote like that. That's a point. And you have to multiply or divide by e from there. I don't know what 2.7 divided by 8 is and stuff. So that's where the calculator is going to get some extra use in plotting those points. So if they're going to do problems like this with us, well, you know, they're going to do problems like this with us. And sometimes a calculator will be needed. But you'll see me progress and graph faster and faster as we go on to questions. Now, logarithmic functions should be brand new to you as far as, well, relatively new to you as far as the last section went to begin with. So we might have to slow this one down more. What I get to talk about pretty quickly is all these are the same, but given now you have a log function, you're taking the log of the thing inside. It's the thing inside the logarithm that's the function. So h is affected inside of that as opposite of. We go 4 units right when it's x minus 4, 7 units left when it's x plus 7. But furthermore, remember log graphs have a vertical asymptote because they're inverses of these other guys, and then they kind of take off this way and go down toward the asymptote that way, something like that. So a couple things we want to keep in mind. I actually start with the vertical asymptote first this time, and that means I start with my h value because you cannot take the log of 0 or negative numbers. When this says log of x minus h, that means x minus h has to be greater than 0. So in this case, x has to be greater than h. That means that x equals h would be your vertical asymptote. So I begin my log graphs with my vertical asymptote in mind. I graph that first, and I do everything in relation to that. Now, I want to talk about other points that I do with that as a result, but I want to first show that in an example because let's just talk the translations. Another point that I do find a reference point k units up or down of here. It's when I take the log of 1. Again, I'll talk about that later, but the log of 1 is 0, so that's a good reset for me. So that's going to be outside of this. Remember, they didn't put parentheses around these, but here's the function, and here's outside of the function. So 3 units up, 1 unit down. You can reflect horizontally, and this would make sense in the fact that if negative x has to be greater than 0, divide by negative 1, x has to be less than 0. That's why we have to graph points to the left. That's why this graph goes to the left, and it flips over that direction there. Negative on the outside is what makes your values negative there. I did some of these in section 5.2 and the log things where I described them. And then horizontal shrinks and stretches. These are the ones that I can't actually pull out of the log function. I can in some way, but it would still be a log on its own. We'll learn those properties later, but like I don't know the log of 4, so I'm not going to change anything with this. I have to maintain these as they are, basically. Log of 4x, I'm going to have to shrink by a factor of 1/4 and keep that in mind, and I'll be very careful with those. And the 1/3 is a stretch by a factor of 3. The vertical stretches and shrinks, we'll talk about those more, but these are pretty easy to do. You do multiply by 5 and by 2/3 and stuff, but you just have to count 5 up each time. Because y is the exponent, we're always trying to increase the exponent just by 1 to go over a certain amount of times over. But now we just get to go up 5 to go a certain amount of times over, or 2/3 to go a certain amount of times over. So we're doing it off easy numbers to work with. So let's look at some examples of this, and they're starting strong from the very beginning here. Let's look at the log of x. Now the way that I would graph the log of x to begin with, the original parent function, you have to remember this is log base 10 of x, and the base is extremely important for how we go about our graphs. When we look at the original f of x, and remember this is scaled by 4s, so this is going to be a little more complicated to talk about. But I start with my vertical asymptote. X has to be greater than 0, so x equals 0 is the vertical asymptote of this graph. Now my first point I do is my reference point, which is where I take the log of 1. It's always 1 away from your asymptote. Doesn't matter if your asymptote's on x equals 4, that would mean 5. 1 away is your asymptote because 5 minus 4 is 1. That's where you take the log of 1. Why am I so intent on taking the log of 1? Because the log of 1 is 0. The log of 1 is 0, and that's something that can wipe out your function. It can turn it into 0. When I take the log of 1, I get 0. That means there's a point on this graph that's 1, 0. That's a nice reference point because everything I do from here on out is in relation to my vertical asymptote and distance from it. This is 1 away from it. The next point I'm going to find will be 10 away from it. Why 10 away? Because 10 is my base, just like exponential functions. So every time y increases by 1, and remember y is your exponent, every time your exponent increases by 1, that's another power of 10 over. We get to go from 10 to the 0 power here to 10 to the 1st over. So when y increases by 1, your exponent, multiply another 10 from your asymptote. This is 1 away. When we go 1 up, now we're 10 away. And remember, this is 10 away because this is 4, 8, and halfway between 8 and 12 is going to be 10. And then we go up another 1 to 2, you're going to be 10 squared away, which is 100 away from there. I can't fit that, so we're just going to have to leave it like that. If you go down 1, you actually divide by 10, so this becomes 1/10 away, and it gets closer and closer to the asymptote as you decrease your exponents. So the range is all real numbers, but the domain is restricted to have to be greater than 0. It must be positive in that case. Now, what your g of x graph is going to do is just it's a reflection of that over the axis. So you can take the graph and do something with that if you want. But I really want to graph these as they are, which is flip this thing over. This is going to be negative 1/2 x has to be greater than 0. Multiply both sides by negative 2 would say x has to be less than 0. That's why we graph to the left. So we take the log of 1. In this case, you actually have to plug in negative 2 to get the log of 1, because negative 1/2 times negative 2 is positive 1. So 2 over, because it's a horizontal stretch by a factor of 2, 2 over gets you 0 out as a result here. And then each time, this is log base 10 as well, each time you go up 1, you are going to multiply by 10 over that way as well. With the difference, not 10, but 20. 10 times 2, 10 times 2. 10 times 2 is 20, boom, so you're 20 away there because you are stretched by a factor of 2, and 2 was already considered in your stretch right there. So it keeps going that way, and divide by 10, 2 divided by 10 is 1/5, etc. We get those points. Are you lost? I'm sure you are. I'm very sure you are. I'm doing a lot of babble, whatever. You're like, I got to click off this video. Hey, you do what you got to do. You can also use a table, but keep in mind, if you plug in random numbers like 3, 4, 5, 6, 7, first of all, you won't get actual numbers, but even negatives, you're just going to get random decimals each time. You got to plug in values that you can take log base 10 of that will become good integers. You know what numbers are good? Powers of 10. That's why I keep saying you multiply by 10, you multiply by 10 when it's base 10. The base matters. Let's look at part B here. Log base 1/2 of x. Okay, 1/2 is your base this time, so that will mean some form of decay in a way where you multiply by 1/2 each time your y increases by 1. But first we start with our asymptote game. On this graph here, your vertical asymptote is at x equals 0 for the same reason. X must be greater than 0. You can only take log of positive numbers. When I take the log of 1, regardless of base, when I take the log of 1, I get 0. So take a look. There's a point here that's 1, 0, which makes sense. Now, from here, every time y increases by 1, your exponent, that's another power of 1/2 multiplied into your set. So you increase by 1, multiply by 1/2. Increase y by 1, multiply by 1/2. Half of a half is a quarter and is an eighth, etc. You go down by 1, you're dividing by 1/2. That's 1/2 to the negative first power, or times 2, which is now 2. And times 2 again is 4. And we complete our window in our graph there. This next one takes the same thing, only there's a vertical stretch and there's a translation 4 units to the left. If you keep in mind with regard to domain here, x plus 4 must be greater than 0, so x must be greater than -4. That's why x equals -4 is your vertical asymptote. Now from here, what value do I have to plug in to take the log of 1? Well, 1 away from here, which is -3. -3 plus 4 is 1, log of 1 is 0. So when I go 1 away from here, I'm at 0 again. The only thing that'll change this from being at 0 is if you have a vertical translation, and this doesn't have any. It has a stretch factor. That doesn't matter. 0 times 2 is still 0. Now, from here, again, there's a vertical stretch of this 1/2 essence. Instead of going up 1 to take half of what we had before, we have to now go up 2. Your y's will be doubled. Your exponents will be doubled what they need to be to take half of what you had before. So go up 2 to take 1/2, another 2 to take another half of that, another 2 to divide by 1/2 or multiply by 2 like this, and down another 2 to multiply by 1/2 like so. So I can do these graphs pretty much at a drop of a hat like that, understanding my transformations, the bases of these functions, no matter which thing I have. E and natural log will take a little bit more time to do based off 2.7 being squared and stuff like that, and then divided by 4. It's going to be a little weird. I'm probably going to use the calculator for that, but that's something I just want to point out. Okay. Writing a function, I'm going to go very fast on these ones. These are no different than what we had before. Just understand where they get put in your function. If f of x equals 2 to the x power, understand that when we're doing a reflection in the x-axis, that's going to be affecting your y value. It takes opposite of that. Keep in mind that 2 to the x is technically going first before the parentheses, so the negative's on the outside of that. And then translating 4 units to the right is an x minus 4. It goes inside the function because it replaces x. X gets replaced with x minus 4. It's all in the exponent. There's the equation. Not much I can say on that. Transformation of log equations. Let's go 2 units up, followed by a vertical stretch by a factor of 2. 2 units up is the plus k. That's on the outside of your function. So whatever your original parent function is, or your original function is, we add 2 to it. Remember, if there are parentheses, it's around the x, not around the plus 2. And then if we want to double that thing, remember, stretch by a factor of 2 after the translation. That means everything gets doubled. That includes the 2 from translation. Instead of translating up 2 units, now we got to translate up 4 units. And 2 times this comes into play there. That would be the appearance of the final answer, I suppose. So not much I need to say on those ones there. They do have appearance of the graphs. I'm going to leave them. But there those are. So we didn't get to look at any natural log graphs, but remember, natural log will be log base e. That way, therefore, we have to multiply units of e out from there. Let's hope that this video serves you very well with what you do. If not, follow what your teacher talks about. Use the graphing calculator, whatever it is. But keep in mind, you want to plug in powers of your number in order to find perfect values out. Log base 10 of 6 will get you nowhere. Log base 10 of 60 will get you nowhere. Only 10 and 100 and 1, and things will actually get you somewhere. All right, let's start with the vocabulary and core concept check, and then we got to go up to, I think, problem number 56, I think it was. Maybe 53. I think it was 56. Given the function f of x equals a b to the x minus h plus k, describe the effects of a, h, and k on the graph of the function. Well, it's no change from what they were before. They're the same letters, but really it's what they do to the graph. A represents, technically, the vertical stretch factor of the graph. What I do with it is a little more than that. It helps with my reference point. I go a units up from the asymptote after translating h units over, because I know that translated h units over is where I'm raising b to the 0 power to become 1. So a is the only other thing that's affected up from k. So a represents that. B is the growth factor, by the way. That's what we use to get all the other points after that. H represents the horizontal translation of the graph. Now, keep in mind, that happens because in the exponent, we want to plug in h for x to get 0 as the exponent to make b to the 0 become 1, to make it kind of wipe out and be irrelevant. K represents the vertical translation of the graph. Now, for me, that's all about the horizontal asymptote. Horizontal asymptote starts at y equals 0. If there's a plus k, now it's at y equals k, wherever it is. And everything I do is in relation to that asymptote. Okay? I want to make sure that that's very well understood. All right, number 2, complete the sentence. Shrink this thing. Complete the sentence. The graph of g of x equals log base 4 of negative x is a reflection in the blank axis of the graph of f of x equals log base 4 of x. So it's a reflection in the y-axis. In the y-axis. It flips horizontally. Now your domain goes from x has to be greater than 0 to x has to be less than 0. Now we have to graph points to the left of it to take log of positive numbers, regardless of base. That's what it's going to be, log of positive numbers. Okay, we're going to start with the set here, the problem set. Keep in mind, I'm going to attach graph paper down below, and keep in mind, I'm going to be graphing my way and explaining that with it. Basically in a tableless format. Even if they ask us to graph each function or something like that, I'll try and explain them away as we go, from parent function to otherwise. So hopefully that's all going to make sense to you. Let's go ahead and get started with this. Numbers 3 through 6, we're going to match the function with its graph and explain our reasoning. Well, this is all about our transformation. So all of these, I want you to keep in mind, guys, they all have 2 to the x power. So that does mean that your y values will be double the distance from the asymptote every time x increases by 1. There's no change in that kind of growth that you see there. The difference is, for me, where a reference point begins and where the horizontal asymptote is from there. So the first one, number 3, is f of x equals 2 to the x power, x plus 2 power minus 2. Now, before I do their official graph and matching it and such, I just want to show you the original parent function and keep in mind what this is going to look like from there. Let's just look at some y equals 2 to the x power. For me, that would mean a horizontal asymptote at y equals 0. This is technically 1 times 2 to the x power, which means that we go 1 unit up when x is 0. 2 to the 0 is 1 times 1 is 1. And every time x increases by 1, it's another times 2. So times 2, times 2, times 2, etc. Now, the first point that I plotted is my reference point. The reference point, guys, is what I'm going to seek most with regard to translation. I want to find the one that's going to be 1 unit up from the asymptote. That'll tell me how I'm translating on h. So on this one, this is 2 to the x plus 2 power minus 2. As far as translation goes, this is going to translate 2 units down. Now, every point's going to translate 2 units down from that as well. Let me not bring the green with it. Everything's going to translate 2 units down as well from that, so the graph would look like this. However, the plus 2 means we also translate 2 units to the left. I'm going to look for a graph that looks like this, where my reference point is 2 units translated to the left when I'm 1 unit up from the asymptote. So which graph does that? As far as this goes, that's 1 unit up, 2 units to the right. It looks like it's going to be C. 1 unit up, translated 2 units to the left. This graph is going to be C. Okay? So that's how I'm going to go about doing these problems, and hopefully that's making some sense here. Whoops, I did a lot of undos. I'm trying to find a way to bring this graph over to the next problem, but we're just going to have to work one problem at a time. Number 4. G of x equals 2 to the x power, x plus 2 power plus 2. By the way, my explanations are in my words, and it has to do with h and k, how we're translating. So I'm going to copy and paste that other graph. I know it's going to be a little off from what I eventually want here, so let's kind of move it. So we started at this area right here for 2 to the x power. We're going to translate this thing 2 units up, and then the plus 2 is 2 units to the left. So my reference point when I do these graphs is I'm going to go 1 unit from the asymptote when I'm 2 units to the left like that, and then I double my distance like this. So we're looking for that graph. That looks to be D. D looks to have that match on number 4 right there, where we are 1 unit up and 2 units, or 2 units up, 2 units to the left, like that. So this graph number 4 is D. Number 5, we have h of x equals 2 to the x minus 2 power minus 2. This means 2 units down and 2 units right. Hopefully you can recognize which one that will be, especially on the 2 units down portion. Looks like it's going to be A, but how come? Let's check it out. So for this one, we can take some graph. The minus 2 is horizontal asymptote is 2 units down, so it'd be here. I want to plot a point 1 unit up from here when I go at x equals 2. 2 units to the right. That'll give me an exponent of 0. So I'm looking at that. That looks like A shares my sentiments exactly on that one. And of course, it doubles the distances because those are the options. These are all with 2's. And then lastly, number 6 looks like it's going to be B. Let's just talk about it with the graph that's on there instead of doing the translation. On 6, the way that I would be graphing that one, which is k of x, equals 2 to the x minus 2 power plus 2, is I'd graph the plus 2 horizontal asymptote up 2 units, And I would plot a point 1 unit up from here. I do 1 unit up because my a value is 1. 1 unit up from here when I'm translated 2 units to the right. 2 units to the right, 1 up from the asymptote is like that. That's the value you can plug in to make that thing 0. 1 plus 2 is 3. 3 is 1 unit up from 2. And that's B. Okay, so you're hearing some stuff on that. Now, that's not new information for me to talk about these things on exponential functions. I've done them in previous videos of the past. You might have done them in IM1 and IM2 as well. Let's go to numbers 7 through 16. Describe the transformation of f represented by g, then graph each function. Y'all, I am going to be doing the taller graphs on these ones here so I can plot as many points as I can fit. Get prepared, get stoked, get hyped. Let's go. All of these parent functions look to be different except a couple e to the x's. So when I get one of my e to the x graphs, I probably got to copy and paste it over. All right, f of x equals 3 to the x power, and g to the x equals 3 to the x plus 5 power. So as far as description goes, this is just a translation 5 units up. The graph of g is a translation 5 units up from f. So that's the description of this. Is that all? And then graph. No domain range. So for 3 to the x, right here, we start with an asymptote at y equals 0. The a value is 1 when x is 0, y is 1. And the b value being 3 means every time x increases by 1, you triple your distance. 1 times 3 is 3. 3 times 3 is 9. Notice I'm counting distance from the asymptote, not distance from my previous point. 9 times 3 is 27, which I can't fit. 1 divided by 3 as we go to the left is 1/3, and then 1/9. And this graph kind of continues in that path. So 17 is up here, not quite 27. I can't fit anything more than that. Here's my original parent function, f of x. My g of x I'm going to do in blue. Now g of x should be the same graph as this one, with one massive exception. Every point is up 5 units. So if every point's up 5 units, I could copy and paste that, but I want to do this one with you at least a few times before we maybe make some changes. We're going to go 5 units up this time. And again, 3 to the 0 is 1 plus 5 is 6. 6 is 1 unit up from 5. That's why I go 1 unit up from here. Times 3 is 3. 1 times 3 is 3, not 6 times 3. We're not tripling 6 because remember, we're tripling 1 and then we add 5 after. I've already accounted for adding 5. I'm going from the asymptote. 3 times 3 is 9. 9 up from 5 is 14. So we get that one and then divide by 3, divide by 3. So this is a translation. This is a translation 3 units up, 5 units up, excuse me, with a growth factor of 3 on this. And hopefully you're getting that feel that this graph is merely just a translation. If I did take and kind of dragged it upward, you know, it would match that one, ideally. It's supposed to. And that's what that one is there. All right, number 8. Number 8, we have f of x equals 4 to the x power. It only gets taller from here. And g of x equals 4 to the x power minus 8. I notice all these ones are just translations to begin with. So yeah, eventually I'll probably play the copy-paste game. Maybe on this one we could... I don't know. We'll plot points on this one. All right, let's see. With respect to graph, it's going to look like that. Now it's just a translation 8 units downward. So the graph... What does f look like? Same as the previous one when it comes to y-intercept, it's still 1, because 4 to the 0, anything to the 0 power is 1. Now we've got to do times 4, though. Times 4 is 4, and times 4 is 16. So it gets a little bit taller based off that growth factor. Divide by 4 is 1/4, and then 1/16, way too small to be able to do something with. When x is 3, y is 64, way too tall to do something with. So here's our original graph like that. Now our next graph is going to be translated 8 units down. So my horizontal asymptote will be at y equals -8 like this, and the same things will apply from the asymptote. I go 1 unit up on the y-intercept like that, and then I do times 4 from here and times 4 from there. 16 up from -8 is +8, so I can plot that point. And I still won't be able to reach that 64 from here, still way too tall. So from here, I'm just going to do what I can and finishing that off. It's just going to work its way up very slowly over time. I need absolute stillness and silence to get that right. Okay, so there's that graph. Now, numbers 9 and 10 use e to the x. You can bet that I'm going to play a copy-paste job with these ones because e's a decimal and I get to use it twice. So with this one, guys, on my translations, I'm just going to go down and up from copy-paste version of it. You might have to plot the points that we have. I'll talk to you about them. F of x equals e to the x power. Let's start with just that graph itself. Hope you don't mind. So e to the x power is the same thing as any other one, only we multiply by e. It's around 2.7, and I'll tell you what those decimals are as well. So we'll get this graph ready to go. Now, e to the 0 power, just like anything else, is 1. That doesn't change. But 1 times e is e. That's around 2.7. E squared is around 7.4. It's around 7.38, literally, but I'll put that. And then e cubed is around 20.1. Now, so this is 17, 18, 19, 20.1-ish. Probably is about right there. A little too tall, but just giving you the idea of placement, that where it would fit. 1 over e, 1 over 2.7-ish is close to a third. A little bit more than a third, but it's looking like that, and kind of do what you got to do off of it. So there's my e to the x graph, and I can use that on my other versions of this graph, and that includes my translations, because that's all we're doing, just vertical translations right now. Just vertical translations. So I'm going to take that graph like that. I want to get this copied and ready to be reproducible. So I'm going to bring it over here. I'm going to group her up and a lot of other things like that. So I'm just getting it ready to go for future problems. Now, what I'm going to do with this one as well is now I'm going to copy and paste this thing because I'm going to do a translation of this, okay? We're going to take this graph and we're going to translate it somewhere. We're going to go 1 unit down. I didn't write down the other part of the problem mistakenly, but I'm translating it 1 unit down, showing you exactly what it's going to look like there. So g of x equals e to the x minus 1. And guess what? If I drew it myself, it would be confusing looking. And this is, for you, probably also confusing looking. So the graph of g is a translation 1 unit down from f. Now, this looks like these intersect all these points here. That's just because of the thickness of my marker. If you actually had this on a graphing calculator and zoomed in, you would see they never intersect. It would be impossible for them to intersect. In fact, look at the points we have. Everything is 1 unit down from here. This was 1 unit up from the asymptote, but 1 unit down from there. This is 1 unit down from here, 1 unit down from here. How can they be hitting each other if they're exactly 1 unit down every place from where they were before? Take your y value minus 1. So they're never actually truly intersecting, even though it looks like, oh, it's catching up to it. Well, it's staying 1 unit down no matter what, but that is the graph of the other one. So this is e, 2.7 up from the asymptote, e squared, 7.4 up from the asymptote, and 20.1 is probably at that tippy top. All right, there is number 9. Let's go to number 10, where I am going to use the same parent function. So number 10 will be f of x equals e to the x power, and g of x equals e to the x plus 4. Oh, not plus 4 right there. So this one, let's paste that original parent function graph like this. Can I ungroup it now? Yes, I can. So from here, we are going to translate this thing 4 units up. So the graph of g is a translation 4 units up from f. So what do? We take this graph, we put the asymptote 4 units up, we put 1.1 up from there, and we go times e times e times e over and over from right here. So this would be asymptote there, 1 up from there, and times e from the asymptote, times e from the asymptote, etc. And you can see a little bit more separation in distance. Every point from blue is 4 up from black. You can clearly see it on this one, and this one, and this one, and this one, etc. So that should be number 10. Numbers 11, 12, and 13. Actually, this goes all the way to number 16. It's just on the next side of things. So we have a few more graphs to do for sure. But these ones are now looking to be horizontal translations, even a couple of reflections here and there. So get ready. Number 11 is f of x equals 2 to the x power. One of my favorites because you can actually plot some more points on this. And g to the x, I'm going to kind of restart everything with respect to graphing that on my own. 2 to the x minus 7. So let's get the graph paper ready. The graph of g is a translation 7 units right. We're going to go 7 units to the right. The graph of g of f from f, however you want to put it. Yeah, f of x, the original. The OG, 2 to the x. 2 to the 0 is 1 times 2 each time as we increase. So double it and double it. 4, double it. 8, double it. 16. Divide by 2 is a half. Divide by 2 is a quarter. Divide by 2 is an eighth. Half of a half, half of a quarter, half of an eighth. Here's your original f of x parent function. And we're going to translate this thing 7 units to the right. Now, I'm going to draw it from scratch. My drawing will begin with the horizontal asymptote. The plus k is plus 0. That means it's on the x-axis, y equals 0, just like this one is. No change there. However, we have to plug in 7 for x to make 2 to the 0 become 1. To reveal your 1 as it is, this needs to become 7. 7 units to the right. 6, 7, that's what makes you go up 1 right there. That's what makes it translate 7 units to the right. From here, when x is 8, 8 minus 7 is 1, 2 to the first is 2. That's why we double from there. And times 2 is 4, and times 2 is 8, and I'm running out of room. I can divide by 2 going this way. So I did one, I won out of range. I did run out of window range there. So you won't be able to see the 16 or anything like that. But that is the idea, the essence of the graph that we have. Same graph, translated 7 units to the right. That starting point is crucial. Not crucial, my success. Listen, you can plug in whatever you want, but I want all my letters to matter. My A, H, and K. My K was my asymptote. My H is my translation this way. My A is how far I go up from the asymptote to start with. My B is what I multiply by each time that I go on. I can do it completely without a table. I don't have to substitute a single value into there, ever. Ever. Period. All right, number 12. 5 to the x. Pretty tall. Pretty tall. And then 5 to the x plus 1, the x plus 1 being inside the old exponent there. So this might be one where I just copy paste the graph over. This graph is tall enough as is. We won't really be able to plot too much anyway. But we got a horizontal asymptote at y equals 0. And then we go up 1 unit here. 5 to the 0 is still 1. And we multiply by 5. We get 5. And next we get 25. This is 17. I won't be able to fit 25 up from there. Divide by 5 is 1/5. That's pretty small as well. So this is a pretty freakishly tall graph. It's going to find its way up to 25 eventually, but not quite yet. Do not pass x equals 2 unless you plan on plotting the point for x equals 2. That's the way that I go about it. That's the way I like it. So there's the original graph. Now, the next one is translated 1 unit to the left. You have to plug in -1 for x to get 1 back out for y, the same as the other one. That's why we go there. There we go. Give it a little space. So let's take this graph, copy paste it, move it 1 unit to the left, make it blue. And this graph is basically going to be starting just 1 unit over here. Instead of being where it is, let's go 1 unit to the left like that. And then boom, now we start there instead. Times 5, etc. But -1 plus 1 is 0. 5 to the 0 is 1. That's why I like to start at that point. 1 unit left. There's the graph. Number 13. So I'm going right at it. E to the -x. I could copy paste my graph. I could flip it over. I'm thinking about it. I can do this quick enough. This is fine. To remind you, negative exponents means division. Another rewrite of this, if you'd like to, it's 1 over e to the x power. Just to show if this was a 2, it's 1/2 to the x power, what you multiply by each time. Or you could call it a reflection in and of itself, horizontally across the y-axis, right? So that's what's happening. Either way, understand this is decay, not growth. So there are still multiples of e, or powers of e, I should say, that are going to the left as x, as x decreases, it gets bigger. That's the only thing. E to the 0 is still 1, no change there, but we have to divide by e as we go this way. A little more than a third, a little more than a ninth, whatever you want to call it. Divide by 1 over e, or, multiply by e here is 2.7-ish, and then 7.4-ish, and then 20.1-ish if you'd like to go so tall up there. But there is this graph, and the +6 will mean we're going to translate 6 units up from this graph. This is the original function, and from here 6 units higher will be g. So the graph of g is a translation 6 units up from f. Let's write it. Let's copy paste it. We'll be good. I don't know what comes knocking on the other side. Problems 14 to 16. All right, so let's get her done. Excuse me, sir. Do you mind if I duplicate you and make you blue? So we're going to go 1, 2. I'm looking at the asymptote, really. 3, 4, 5, 6. Asymptote is now at y equals 6. And there's the equivalent graph in that form. Hopefully exponential functions are making some sort of sense with the graph without a table. Whatever you got. Okay, this is also e to the negative x, so I am going to copy and paste this one. Hope y'all don't mind. I don't know how to with this thing here. Give me a second. I guess I can erase what's there afterward. I just don't want to do it again. So I'm going to copy paste this thing. I have to get rid of blue now, sort of, somehow, without getting rid of black. So let's see. Ooh, without getting rid of black. Deselect some black. I don't know how to do this. Shoot, I'm playing with this more than anything else to try and get this in place. I don't know if I can. Let me pause and fix it. Okay, that actually took 2 seconds. I could have stayed on camera for that. Okay, let's do number 14. F of x equals e to the negative x. G of x equals e to the negative x minus 9. This is a translation 9 units down. In fact, I can even copy paste this one so my typing skills don't get in the way. 9 units down from f. So we have to do the same graph here. And this is our last e to the x graph, so I don't have to worry about copy pasting anymore here. But copy paste this guy here, and I'm going to go 9 units down from here. Let's go blue. Let's go down to negative 9 on our asymptote. Make sure you don't horizontally translate that thing at all. And there is this next graph like that. Now 20.1 actually fits this time. Was that 20.1? Let's see. Here was negative 9, and it should actually be a little bit higher. I guess it should be up here at 11. So 20.1 is probably a little more like that. Oh, when x is negative 3. It should probably be around right there. There we go. Okay, close enough for me. Okay, number 15. We have a couple decay values, 1/4 and 1/3. Remember, if it said 4 to the negative x or 3 to the negative x, it would mean the same thing in that way. So number 15, we have f of x equals 1/4 to the x power. G of x is 1/4 to the x minus 3 plus 12. Okay, we got a couple things going on here. It might be worth doing the entire graph with you, with that in mind. So let's get this one set and ready to go. Let's start with the 1/4 x graph. This guy will be the opposite of the 4 to the x that we had in one of the original problems that we started with. Now 1/4 of 0 is still 1. No change there. It's just you now multiply by 1/4 as you increase by 1. So 0.25 and, 1/16 over. Divide by 1/4 or multiply by 4 as you go this way. So up to 4 and up to 16, and it's a decay of a graph here. This one is a decay. Now, the next graph looks a little bit tall or high up. This one's going to be translated up 12 units and right 3 units. So I got to go up with the horizontal asymptote of y equals 12. I'm not going to fit that 16, not even close to it. And we're going to go right 3 units before we get up to a reference point of 1 here. This is your times 1/4 and times 1/4 happening here, and divide by 1/4 or multiply by 4 going up there. That's really all I can fit. I'm not going to be able to fit that 16 units up, but here's my new graph with that reference point being right here from where it was right there. It's up 12 units and right 3 units. So the graph of G is a translation, 3 units right and 12 units up from F. Okay. And then number 16, ooh, minus 2/3. That's nobody's favorite. We're going to have to deal, I suppose. Number 16, we have f of x equals 1/3 to the x power, and g of x equals 1/3 to the x plus 2 power minus 2/3. Okay, so for this one, 1/3 to the x power, same as the 1/4, only we multiply and divide by, well, 1/3 or 3, however you want to say it. Y-intercept here times 1/3, and then times 1/3 is 1/9, working that way. Divide by 3 is 3, and then 9, well, divided by 1/3. is 3, 9, and then 27. Unfittable. So there's our orig. Now this next graph here, we're going to have to translate 2 units and go down 2/3. This is going to be the no fun version of this one here. 2/3 down. It's not much further down than this right here. Somewhere between 0 and -1. Somewhere between -1/2 and -1, like that. So these counts are going to be a little, I'm just going to have to go 1/3 up from -1, I suppose. Now, we go 2 units to the left as well. 1, 2 to get 1 up from there. Okay, if you plug in -2 right here, you're going to get positive 1/3 as a result, is basically the way I'm saying that. Now, from here, you got to take 1/3 of this number. Yeah, this is going to be a little kind of tricky. And then you got to divide or multiply those by 3. So 3 up from -1 is 2, and then just go a little bit up from there, right? I'm going to go from -1 technically and count 1, 2, 3, and then go up 1 from there. So 9 up from -1 is 8. Here's 8, and then 1/3 up from there is that point, and I still can't fit the 27. So not a fun graph with that being taken care of, but still the graph nonetheless. Now I still have to describe it. The graph of G. 2 units left and 2/3 units down from F. Okay, there are those graphs. Let's move from 17 to 24. Describe and graph these ones. These are going to be more so horizontal and vertical stretches and shrinks. Maybe a little couple translations here and there. Let's see how tough some of these ones get. The ones with E and stuff, I'm tripping over a little bit. Actually, we start with E. Let me steal my parent function graph from before on e to the x. Give me 1 second. I'm going to find that one. It was right here, so I got it. And if there are e to the negative x's, I might just flip it over. Hope you don't mind. Because this is just the original graph. So here's my original graph for f of x equals e to the x, g of x equals e to the 2x. Don't worry, I can't copy and paste this graph and do something with it because now it's stretched. Or actually, in this case, it's shrunk. The 2x means you need x's to be half of what they were to achieve the same x value out as before. So the graph of g is a horizontal compression. Wait, 2 to the x? Oh, e to the 2x, not 2 to the 2x. I'm sorry. E to the 2x. Now, there are a couple ways I can talk about what it is we're doing there, but it's still, yeah. Anyway, the graph of G is a horizontal compression or shrink by a factor of 1/2 from F. So we're going twice as inward from there. We have to plug in 1/2 for x to go e times up and 1 for x to go e squared times up, things like that. I mean, think about your table. When x is 1, y is e squared. That's how it works. E to the 0 is still 1, though, and your horizontal asymptote is still here. No change there. E squared is still 1, only now it's half this from before. So now, to get up to 2.7, you got to go halfway over. That looks more like 2.5. But 7.4, you got to go halfway over to 1. 20.1, if it's truly up there, you got to go halfway over. Instead of 3 over, it's 1.5 over. So it's like that. Go 1/2 over to divide by e and another half over to get that one. So it's a horizontal shrink. Horizontal shrink. Another version of this that you could do, although you get half the points out from it, is you could turn e to the 2x into e squared to the x power. So every time x increases by 1, you go up another power of e squared, which means you'd hit this point, and then you go up another 1 and you can't fit it anyway. So I guess that doesn't really work as well as the original. So there's that. Number 18. Number 18, this is where I might have to go to the calculator. I am going to copy paste the original parent function and just kind of talk about those. Maybe we can use it off e. Maybe I can go without a calculator. F of x equals e to the x power. G of x equals 4/3 e to the x. And honestly, look, they would use a calculator as well, or they just say just graph it from the graphing calculator. I just don't know what their full intentions are with this. If this was not an e, I'd be a lot happier even with the 4/3. But the graph of G is a vertical stretch by a factor of 4/3, about 1 1/3. 33% larger than it was before. Now this time, this is where a changes. Listen, when x is 0, e to the 0 is 1. That's great. But 1 times 4/3 is 4/3. Everything is 4/3 taller than it was before, including our reference point. Before we were 1 up, now we're 4/3 up. Not much taller, 1 1/3 up instead, but it's like that. Everything's 4/3 taller than it was before. What's 4/3 of e? I don't know. I'm going to go to the calculator for that. 33% taller. So I'm going to do a few of these. 4/3 of e is going to be 3.6-ish. So this is around here, 3.6 instead of 2.7. Oh, I should have known that one. 7.4, instead of that, it's going to be really close to 1, or 10. So I'll just say really close to 10. That's about 4/3 up right there. Because 0.75 would be 3/3 of the way up. Another 4/3 is another 0.25, so really close to 10. And 20.1 I can't fit. Another 4/3 up from there, sure, and just a little bit taller, guys, not significantly. Vertically stretched by a factor of 4/3 is this guy. It should always be above the other things by 4/3 the factor. Okay, number 19. Good, no e, and I feel much better about this one. Number 19, f of x equals 2 to the x power. I'll even graph the original as it was. And g to the x equals negative 2 to the x minus 3 power. Oh boy, oh boy. Okay. The original 2 to the x graph is right here. Double, 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 double. 1/2, 1/2, 1/2. All right, here's our original function. We're going to do two things with it. Let's type it out first, then we'll graph it and see if it all aligns. So this negative is in front of the y value. It's not b, it's a. It's a -1. The graph of g is a vertical, is a reflection in the x-axis, followed by a translation 3 units right of f. Now, the way that I'm going to be doing this one here is, first of all, there was no vertical translation, so your horizontal asymptote is still y equals 0. So I'm going to go boop, 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 boop. Now, this is also -1 times 2 to the x minus 3 power. I need to keep stressing that that negative is not 2 being negative. It's a -1 multiplied in front. You can't have the 2 negative. It's not possible to have the 2 negative and be an exponential function. So leave that. What I'm going to do is, remember, -1 means I'm going to go a units down instead of a units up from there. So instead of going 1 unit up plotting this point, we're going to go 1 unit down. But not right here. We got to go 3 units over to plot the 1 unit down. So this is where I'm going to start. Now, every time x increases by 1, you still double your distance, but it's doubling 1 unit down to go 2 units down, and doubling that when x equals 1 to go 4 units down. You can plug in these values for x and confirm that these are the values for y you should get. And then 8 units down, and then 16 units down. Divide by 2 to get 1/2, 1/4, and 1/8, etc. as you go to the left instead of to the right. So this graph is going to look like this instead. So I will circle my reference point, but this should indeed be a reflection in the x-axis, flipped over, and translated 3 units right. This is where I began. I didn't need to plug in 3, but if you do, you will get -1. Fun, fine graph. All good with those. Number 20. We got a lot we can do on number 20, and I can try and talk about all of them if you like to. But number 20, f of x equals 4 to the x power. And g of x equals 4 to the 0.5x minus 5. Okay, lots to say here. First of all, I'm going to start changing g up a little bit. I'm going to first turn that thing into a 1/2. So it's 1/2 to the 1/2 x minus 5. Now, if I factor 1/2 out of there, which might be important, factoring a 1/2 out of there turns this into x minus 10. Remember, if I distribute a 1/2, 1/2 of -10 is -5. This is crucial because your translation is not 5 units to the right. It's 10 units to the right. Remember, the value of x that gives you 0 is your translation. That's one bit of this. The next bit of this is the 1/2 can either be referred to one of two ways. Either a horizontal stretch by a factor of 2, or you can treat this as 4 to the 1/2 power, which is the square root of 4 raised to the x minus 10, and the square root of 4 is 2. My personal version of this graph that I would love more than anything else for g of x is this, 2 to the x minus 10 power. I know the parent function out of 4 there. That's the only difference of why you might not want to do that. It's all up to you based off that. But you'll see here, whether you do it this way or this way, you're going to get the same answer. But yes, absolutely factor that 1, or 0.5, whatever you want to call it. Absolutely factor that 1/2 out from there as you go and do this. So one of two descriptions. It's up to you. It's either, I mean, I probably have to describe it from this one, because that's going to make, instead of just saying, oh, it's 10 to the right, because it's not just 10 to the right. This is now a brand new growth factor, right? So let's describe it based off that first one. The graph of G is a horizontal stretch by a factor of 2, followed by a translation 10 units right, not 5 units right. You could say this. You could say a translation 5 units right followed by a horizontal stretch with a factor of 2. But then that 5 will also be stretched into 10 if you describe the translation first. You may do that. That's probably, honestly, that might be what the book does. Honestly, that might be what the book does. But I go more in the form of this, and honestly, I really go in the form of this. So the original graph of 4 to the x power is here. 1 times 4 is 4, times 4 is 16, divided by 4, and divided by 4 there. So here's our ridge. Now, the problem with this graph is we go 10 units to the right. My window range is not really good for that. So I'm going to have to just make stuff up. But if I do it based off this one right here, then I can say, you know, x equals 10 is already over here. Guys, we're already like off the graph. When we go 1 over, it's times 2, and another over, it's times 2 like that. I want you to imagine that these are still here. So we hit 8. We hit 8 when you go another over, and then 16 up there. So I'm doing what I can to pretend like they're there. And then half and half and half, etc. Let's see how this matches my other graph where I'm saying 4 to the 1/2 times x minus 10 instead. What we would do here is we'd hit the same points, only we'd only hit half of them because we got to stretch it by 2. So I start from this point still as well. I'm 10 units to the right when I go 1 unit up, but I have to go stretch by a factor of 2. That means I have to go 2 over before I multiply by 4. I go 1, 2 over to multiply by 4, and another 1, 2 over to multiply by 4 there, and another 2 over here to divide by 4. So I still hit those points. My 2 to the x actually hit double the amount of points than the 4 to the x one hit as a result of that. But that graph is still the same one. So tricky problem all told the way that they wrote it, but it still works the way we'd want it to. All right, let's go to number 21. We and 22 are both e to the negative x. I'm going to steal that parent function again and just flip it over. So 21 is f of x equals e to the negative x. Let's start by pulling that one over. I have to find it. I think it was this one. Yeah, this one? Okay. So let's steal this. There's our e to the x. E to the negative x. I'm just going to flip it over. All right, there's our e to the negative x. Okay. G of x equals 3e to the negative 6x. Nothing fun about what we're about to do here. Now, the negative is still negative, so there's no reflection to be had that wasn't already there. But there is a 6. Wow. There's a 6 here and a 3 there. The 3 isn't raised to that 6 power or anything at all. It's just e. So, guys, I don't know how I'm going to graph this one. The graph of G, this is going to be so tall. This is going to be so tall, it's like not even going to matter. The graph of G is a vertical stretch by a factor of 3. Followed by a horizontal compression by a factor of 6. Wow. Wow, 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 wow. So that's a lot going on to this thing right here, yeah? So, okay. E to the negative x is there. 3e to the negative x. First of all, it's stretched by a factor of 3. When x is 0, this becomes 1 times 3 is 3. So that's one difference. Everything is 3 times taller than before. But it's not just 3 times taller. We will do 2.7 times 3 to get around 8.1. But we got to go 6 times compressed to make that work. So 8.1 would be here. We got to go 6 times compressed. That's about right there. Guys, this thing is shrunk. This thing is shrunk. This thing is like that. This is going to be super tall. I got to go 7.2 or 7.4-ish times 3. 7.4-ish times 3 is already 22 point something, which is off the graph. but I go 6 times smaller from that as well. 22 off the graph is probably about right there. This graph is going to be so freakishly tall. If I multiply 1 over e times 3, that's actually a little bit more than 1. Okay, it's a little bit more than 1, but I go 6 times in to get that 1. So it's around there, a little bit more than 1, but 6 times inward. And then divide that, it was like a little 1/9 times 3 is okay, a little 1/3, but 6 times less right there. This graph is just kind of off the rails. I guess I could have changed the scaling, but since I copied and pasted from the other one, I'm not going to. But I'm just emphasizing the fact that this graph is too tall for its own good. And it does shrink towards 0, and it does like that, but again, it doesn't cross through. So that's just the other version of that graph right there. Very wicked. What was that? It wasn't from Despicable Me. What was the one where the kid's like, that was totally wicked? The Incredibles. That was totally wicked. And that's kind of what that is there. All right. What are you waiting for?
I don't know. Something amazing, I guess.
I don't really know what they sounded like. I got to see that movie again. Same parent function. A lot of compression. And a little bit of translation. At least there's no vertical stretch alongside what we're going to do here. But take this same thing. Let's describe it. We will do the graph of G is a horizontal compression by a factor of 5. Still pretty tall. Followed by a translation 2 units up. Now I'm going to... Technically, you could translate up beforehand anyway because horizontals shouldn't affect verticals in that way. But I am going to start with the translation regardless. You know me. I'm going to go 2 units up from asymptote. To the 0 power, we still get 1 up from the asymptote like that. But now we're going to take our 2.7. We're still going to go 2.7 up, but we don't go 1 over to get that. We got to go 1/5 over to get 2.7 up. So about right there. 1/5 of the way. That 7.4 up, 3, 4, 5, 6, 7.4 up is 2/5 of the way over. About a halfway over there. 20.1 is 3/5 of the way over. So wherever 20.1 is way up there, it's barely even over there. This is super tall as well. 1 over e is just 1/5 of the way over like that. 1 over e squared is another 1/5 of the way over. Just another super tall graph. It might as well be the same one as before. The translation is actually the thing that's most starkly different from that last one we did. Even though there was some vertical stretch factor on the other one, this one doesn't seem to have that. It's still super tall, guys. Okay. Numbers 23 and 24, we get a little bit less E happy. Number 23, f of x equals 1/2 to the x power g of x equals 6 times 1/2 to the x plus 5 power minus 2. Okay, this one will have the most of what I want out of kind of building character into these graphs, saying like, okay, these are the extent of things you can do that are like normal, Let's describe all the things first and then just see that we can make sense of those. There's A, H, and K going on. The graph of G is a vertical stretch by a factor of 6. No A. Followed by translation 5 units left and 2 units down from F. All right, so those things are going to happen. Now, the order in which I graph them might be a little bit different from how I said that. So, the original graph, 1/2 to the x power. It's like 2 to the x power, only it's decay instead of growth. So we got to go times 1/2 this way and divide by 1/2 or times 2 the other way. So 2, 4, 8, and 16. And our other graph will do the same things, sort of. We will divide and multiply by 2 in that kind of way, but we're starting from a different spot. We have some translations to be had, all that kind of stuff, and it's vertically stretched. So how does this work? I'm going to start with k, -2. This is the most complete version of the graph I can explain for you guys so far, it seems. So -2. I got to plug in -5 for x to raise this to the 0 power, make it become 1. Times 6 is 6 when I'm 2 down from there. So I'm going to go 6 up from -2 when I'm 5 units over. 1, 2, 3, 4, 5. And 6 units up from here is at 4. This is my reference point. I'm going to circle it. This is my reference point. I literally didn't do any actual calculations or table work. Look, you can plug in anything. You can plug in 0, but 0 plus 5 is 5. 1/2 to the 5th power is 32. 6 over 32. Oh my gosh, I don't want to do that. I'd rather start with a good number there that's based off these numbers. Now I get to divide 6 by 2 each time the x goes over 1. 6 divided by 2 is 3. 3 divided by 2 is 1.5. 1.5 divided by 2 is 0.75 or 3/4, and then 3/8, and then 3/16, and it goes down like that. Let's divide 6 by 1/2 or multiply by 2, and we get 12. 12 up from 6 is at y equals 10. And then 24. 24 up from 6. Sorry, 24 up from 4 is y equals 10. 24 up from 4 is, not from 4, from -2. I'm saying numbers wrong. 12 up from -2 is y equals 10. I knew what I wanted. 24 up from -2 is 22. I can't fit that one. Okay, I was going good until I was saying the wrong words. I knew what I wanted to do. I just didn't know how to say it. I speak English, not math. I think math, not English. Okay. There we go. Nice old graph from there. Number 24. More interesting b value than normal. Okay. We have f of x equals 3/4 to the x powered. This might be one that I copy and paste what's here, although I do have to reflect it. G of x equals negative 3/4 to the x minus 7 plus 1. Let's start with that 3/4 to the x power graph. Okay, so let's see how good you are at your fractions and mixed numbers. This is still a 1, as this is still a -1 right there, right? So x is 0, y is 1. We got to take 3/4 of 1 to get 3/4. 3/4 of 3/4 is 9/16. It's a little more than a half. 3/4 of 9/16 is 27 over 64. No, it's less than a half. I don't know. 3/4 of that height, basically. And you can see less of a progressive shrink overall as you go. Dividing by 3/4 is multiplying by 4/3. So 4/3 of 1 is 4/3. 4/3 of 4/3 is 16 over 9, which is 1 7/9. 4/3 of that is 64 over 27, which is about around 2.5-ish. And then you have 256. Wow, how many of these am I going to do? 256 over 81 is more than 4. 4 points, just a little bit more, like that. And then 1024 over 243. Well, that's about 5. It's a little more than 5. So I'm just going 4/3 my previous numbers there. I'm thinking 1024 over 243. That's probably a little lot more, not a little lot more than 5, but that looks like a little more than 4/3 than it should be. So just going 4/3 up from each of these and what we have. 256 over 81. I take that back. That's because this looks weird. That's a little more than 3, not a little more than 4. 256 over 81 is, like that. And then it shoots up higher from there. Okay, that makes a little more sense for me. And then, 4,096 over 729 is a little less than 6. Wait a second. That doesn't make any sense. 4,090... I gotta do these calculations in my head. Now I'm getting all messed up. 4,096 over 729. Yeah, it is less than 6. Well, wait a second. What's... Oh, 729, not 726. But 1,024 is 4 to the 5th. 243 was 3 to the 5th. Oh, that's 4.2. Hold on. That I messed up some of my numbers here. And this is a little more than that one. There we go. This one's a little less than 6. Okay, I'm messing up my numbers here. Apologies. Just getting the graph in as I could. Like I said, how do you do with your fractions? I'm not doing any better with my fractions. I'm trying to do them in my head. Anyway, getting these points. You can tell why I'm going to copy and paste this one as I go. They said 3/4, so I got to go the 3/4 this way. Let's keep going. 4,000, let's see, 4 to the 6th over 3 to the 6th. You can clearly use a table for this one here. I'm going to now use the calculator. Oh, I already did 4 to the 6th over 3 to the 6th. 4 to the 7th over 3 to the 7th. It's a substantial looking graph. Things are going well. All right, 7.5. 7.5. And then 4 to the 8th over 3 to the 8th. You know, I really should have just done this in the table. You can probably use a table for this one, meaning graphing calculator table. 9.9-ish. So a little less than 10. And 4/3 of a little more than 10 would be in the 13s. So I'm just going to graph it like that. That's quite a bit of graph. I'm very, very sorry for my inability to do division before that. I said 1,000. I said basically 1,000 over 250 was 5 instead of 4, and that was the beginning of my downfall. Apologies on that. Okay, here's what I'm going to do. I'm going to group this guy so I have it in place. I'm going to copy and paste it, and I'm going to get ready to use this graph later in a bit. Okay, now, here's what we're going to do. We're going to flip this thing over. Okay, we're going to flip it over. We are going to, right, there's a flip reflection over the x-axis. We're going to translate this 7 units right and 1 unit up. So 7 units right. I'm looking at this point right here that's on here. So I'm going to move this over 7 units to the right like that and 1 unit up. I'm looking at my asymptote like that. And that should be the aligning of that graph there. So that's the other graph. I know I cheated, but that's everything that's going on there. The graph of G is a reflection in the x-axis followed by a translation 7 units right and 1 unit up from F. Okay, my F graphing was terrible with my 4/3. I couldn't take 4/3 of numbers. Super apologies for that. But there is the graph as a whole. Okay, probably finished with some graphs for a while till we hit logarithms. So let's go to some error analysis, 25 and 26. Describe and correct the error in graphing the function. So number 25, they have f of x equals 2 to the x plus 3. Well, I don't see my horizontal asymptote being 3 units up. These are scaled by, that's an 8? Oh, those are going by 2s. So this, we should have a horizontal asymptote up here. What it looks like they probably did, they probably translated 3 units to the left, like x plus 3 inside the exponent. They probably went over here to go up just 1 unit, because remember, these are scaled by 2s. So it looks like they translated left, treating it like an h, instead of translating 3 units up like a k. They translated 3 units left like h, instead of 3 units up like k. So let's correct it. I'm going to do a small version of the graph. I don't really need, I can't go up 27 anyway, so I can fit as many points here as I could. F of x equals 2 to the x power plus 3. The plus 3 is our translation. We're going to start with the horizontal asymptote, 3 units up. 2 to the 0 power is 1. 1 up from 3 is there, and double your distance from there. 4 up. Oh, I'm sorry. We're going times 2, not times 3. But even still, small graph will do just fine right there. So those are some times 2s, and we're good. Okay, let's correct the next error, number 26. Please don't be E. Please don't be E. Please. Oh, thank goodness. All right, f of x equals 3 to the negative x. What I see is a reflection in the x-axis instead of a reflection in the y-axis on this one. So they reflected in x. That would have been what they do if it was negative 3 to the x instead of 3 to the negative x. They reflected in the x-axis instead of reflecting in the y-axis. So same concept of graph here. We are going to flip this thing over this way. This will become decay instead of growth, right? This is y equals 3 to the negative x, which is the same thing as 1/3 to the x power. Now, we just did one of those parent functions before. Again, they have the right asymptote, but this should stay above here. It's positive decay instead of negative growth. So here we divide by 3, 1/3 and 1/9. Doesn't really look like 1/3. 1/3 and 1/9 and stuff like that, and then times 3 and times 3 going to the left direction. So this should be your graph, positive decay, not negative growth. And there's number 26. Okay, we're going to start doing some things with logarithms. It looks like we got to do graphs to begin with. Describe the transformation of f represented by g, then graph each function. Now, we're going to be doing the same tall graph paper stuff I had before, but now they need to be rotated over like this because now we're going to go the long way instead. So with all of these, I got to do some extra work on top of just the graphs. I got to get my domains out of here, which I think domain's going to start pretty simply to begin with here. So on number 27, we have f of x equals log base 4 of x. Let's just begin with this graph before we do anything else from here. Regarding its domain, x has to be greater than 0. You can only take the log of positive numbers. So the line x equals 0 is our vertical asymptote. It's going to look like this. Log functions are inverses of exponential functions. They have vertical asymptotes, not horizontal. When I take the log of 1, literally when x is 1, I get 0. That's going to be my reference point. Whenever I go 1 away or my horizontal stretch factor away from there, I get 0. From here, 4 is my base, which is how much I'm going to multiply and distance myself from the asymptote. Every time my exponent increases by 1, my exponent is my y value. Every time y goes up by 1, I go 4 times further out than before. This is times 4. And then times 4 again as I go up by 1 is at 16 like this. And it should remind you of exponential functions, but all inverted. Down 1 is dividing by 4 and dividing by 4. And then your log function is going to look like this. This is the original. Sorry, I have to find my best way to draw this out. This is the original log base 4 of x function here. It goes down forever. And it gets closer and closer to the asymptote there. That's the graph. Now g of x is 3 times log base 4 of x minus 5. They're throwing you right into the deep end with some of this, where we got to do two things at once. There's a vertical stretch as well as a vertical translation. The graph of g is a vertical stretch by a factor of 3, followed by a translation 5 units down. Now, I technically do the translation first alongside everything I do. The domain is still x is greater than or equal to 0, so there's no change on my vertical asymptote. Okay? So, I still have a vertical asymptote here on the y-axis, on x equals 0. Boom. And the log of 1 is still 0, right? The log of 1 is still 0. 3 times log base 4 of 1 is 3 times 0, which is 0. Minus 5. So here's my translation. Instead of circling right here when I go 1 away, I'm going to go down 1, 2, 3, 4, 5. This is where I'm going to start. Now, every time y increases by 1, my exponent, I should be multiplying by 4 to move along, but this has a vertical stretch. So the y's will become 3 times taller than they were regarding exponents for me to go 4 times over. So instead of going up 1 for times 4, I got to go up 3 to go times 4, like this. And up another 3 to go up times 4 again to get to 16, like that. So it's taller, 3 times taller than the other one. This is my reference point. Down 3 to divide by 4. To get 1/4 and 1/16, things like that. So here's this log graph with my reference point there, and I did times 4 each time, but I had to stretch it 3 times taller in order for that to happen. Your exponents have to be 3 times bigger for you to go times 4 over. All right, number 28. I gotta get that one ready for the next question. Number 28. F of x equals log base 1/3 of x. Let's start with this before we write in the other part. Domain is still x is greater than or equal to 0. You can see there's no change inside there. In fact, they don't start changing until, well, g of x here. So x equals 0, still the vertical asymptote. Log of 1 is still 0, no vertical translation, so we'll be here. But every time y increases by 1, we're multiplying by another 1/3. This is our base value. So 1/3 means a bit of decay as y increases. So 1/3, up 1 is 1/9. Down 1 is dividing by 1/3. That's where you'll get 3 and 9 and 27, which cannot fit. So this original graph looks like this right here. From the reference point onward, we get some good old graph. Now, this g of x is log base 1/3 of negative x plus 6. All right. Domain. Domain here is a little bit different. Negative x has to be greater than 0, so when you divide by negative 1, x has to be less than 0. Dividing by a negative or multiplying by a negative flips your inequality. That means our graph goes to the left, not to the right. We have to plug in negative values for x in order to take log of positive numbers. The plus 6 is a vertical translation. So this is where I'd take the log of 1 to get 0, when x is negative 1. Plus 6 is at 6 right here. This is our reference point. From here's where we do all our base stuff. No vertical stretch change. I go up 1 to multiply by 1/3, and then I get 1/9 here, etc. It shrinks on inward. I divide by 1/3 as I go down to get 3 and 9, and I can't fit 27, but there's the appearance of this version of the graph here. I still have to describe it. I know. All right, that was actually pretty good looking. Okay, the graph of G. Is a reflection in the y-axis, followed by a translation 6 units up from F. All right. There's a description. There's the graph. There we move on. Number 29. Y equals. They're getting even weirder on you. Log base 1/5 of x, and g of x equals log negative log base 1/5 of x minus 7. Okay, the log base 1/5 of x is, first of all, vertical asymptote at x equals 0 for the original f of x function. Log of 1 is 0, and we multiply by 1/5 every time y increases by 1. So 1/5 up and 1/25 up. You really can't fit anything there. Divide by 1/5 as we go over, and we hit 5 here. And then later, though I can't really truly fit, it would be 25 somewhere further out, right? Probably even further out. So this graph goes pretty sharply outward, like so. Just trying, and there's your original function there. G of x has the same 1/5 thing, only some other things are going to happen. First of all, domain says x minus 7 has to be greater than 0. Therefore, x has to be greater than 7. X equals 7 is now actually a vertical asymptote. This is a translation 7 units to the right. Now, the log of 1 is still 0, as in, if I plug in 8 for x, 1 away from here, 8 minus 7 is 1. Log of 1 is still 0 times negative 1 is still 0. So log of 1 is still 1 unit away. No change on that. That's still the same. The difference is the negatives here affect your y's. So in order for your y's to increase by 1, increase your exponents by 1, y's have to be opposite of what they are. Your y's have to go down 1 to multiply by 1/5 instead of up 1. Down 1 times 1/5 is 1/5, and then 1 over 25. And up 1 is divided by 1/5 or times 5. So it almost seems like a regular kind of growth thing. It's like it's doing 1/5 to the negative first power, and it's becoming 5, right? So it's like as if it was log base 5. This would be the same thing as log base 5 of x minus 7, like that. We don't see it that way, but that's what it can be written as. Anyway, so over here, and there are reasons for that. We're not going to talk about. Anyway, so from there, we can do times 5, 1, 2, 3, 4, 5, and then times 5 is 25, which clearly can't be reached. Maybe if it was x plus 7, we could actually reach it. I wish they went that direction, so we could actually fit a 25 over. All right, very sharp, very sharp. There we go. Okay, last one for these log graph things, number 30. F of x equals log base 2 of x. Okay, this one's the most normal one. This is the most normal one. And G, oh, did I describe this one? I'm sorry. Let me first describe this one. The graph of G. I got so hung up on the other explanation. Graph of G is a reflection in the x-axis, followed by translation 7 units from F. Okay. Number 30. F of x equals log base 2 of x. G of x. What the heck? G of x equals log base 2 of x plus 2 minus 3. All right, this is the most normal one, and the most we can get out of our graph as well, because we can get a lot more points from it. Log base 2 of x has a vertical asymptote at x equals 0. The log of 1 is 0 as well. And we double our distance each time y increases by 1, your exponent. Remember, logs, when you take the log of something, you get an exponent out, and we got to double our x values. Log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of 8 is 3. Log base 2 of 16 is 4. Log base 2 of 1/2 is -1. Log base 2 of 1/4 is -2. If you want integers out, you got to know your powers of 2. That's why I'm just doubling my distances every time I know my exponent increases by 1. I'm thinking in inverse form like exponential functions to get them. Even table users will struggle if you start plugging random numbers like 10 and stuff like that. You're just going to get random decimals. Up to you. I don't care for them. Log base 2 of x plus 2 minus 3, we begin with the domain x plus 2 has to be greater than 0. So x has to be greater than -2. That means our vertical asymptote is at x equals -2, shifted 2 units to the left. The graph of g is a translation 2 units left. It's also 3 units down. The log of 1 is 0. I got to plug in -1 for that. -1 plus 2 is 1. But 0 minus 3 is -3. So I shift down 1, 2, 3 units. Here's my reference point. From here, my base is 2. I double my distance from here every time y increases by 1. Go up 1, double my distance. Go up 1, double my distance. 4 away from the asymptote. 8 away from the asymptote is at x equals 6. When I go up, and 16 away from here is at x equals 14, like that. Divide by 2. When I go down 1, divide by 2, divide by 2, and there's that graph. So this is the most basic form of one I would do. Normally, we don't have to graph both of them. I mean, they're requesting it, obviously. But if they just asked us to graph this one, it'd go pretty fast. Just I had to graph 2 of them, so it took a little bit more time. Okay, the graph of G is what compared to F? A translation 2 units left and 3 units down. All right. Most normal. I guess we're not doing natural logs on graphs. Oh, at least not yet. Numbers 31 to 34, match the function with the correct transformation of the graph of f. Explain your reasoning. So they're not even showing you what f of x is. It's basically a black box function. We do know that it's some sort of, I don't know, it's logarithmic. So we're taking a look at what these are in comparison. I might have to do my old copy-paste job of these ones from before and see what we're trying to get out of it. So I'm copying, pasting. I'm going to move this one over alongside these and compare them and say what's going on with one versus the others. I'm just going to try and get them the same size or close to it at least. Hold, please. Okay. So the more transparent one is the original function. We have to think about what this is doing in comparison to it. So when you compare these ones here, and you have to remember, these are all about having asymptotes, right? Logarithmic functions have asymptotes. So if my original asymptote is on x equals 0, you know, the y-axis, this one on A looks like it's translated over to the right. You have to understand that even if there's up and down translation, there's also a left to right, or there's a right translation for this one. Y equals f of x minus 2 looks like it could be A, because this looks like it's translated 2 units to the right from what it was before. These other ones don't go to the right because this asymptote's at x equals 0, and x equals negative something, probably -2, depending on what we're doing. So this is the one that makes most sense to be A because it's a translation 2 units to the right. It says explain your reasoning. Translate 2 units right. Based on the asymptote. The asymptote is now at x equals 2. There's your explanation. And there's the graph on it. Number 32, f of x plus 2, and the thing inside there means a translation 2 units left. I think we saw that one. I think it was D, but let's take a look. That's y equals f of x plus 2. Take your f of x function and do what with it? Move it 2 units left. So is it this one? Nope. That's same asymptote. Same asymptote. Different asymptote. So we go from y-axis asymptote to now x equals -2 asymptote. There's the translation there. So it's gonna be day. Like that for this log function. I'm trying to do this. It's probably easier to type out. Just lazy. I'm just senior lazy there. Translate 2 units left. So there's A, there's D is 31 and 32. Number 33, 2 times f of x. Okay, this isn't even a translation, but it's a vertical stretch. So we got to find out which one is taller versus which one is horizontally compressed as part D. Looks like C is going to be taller. You can tell here that they still have, f of 1 is 0, the log of 1 is 0 kind of thing right there, but everything looks like it's twice as tall as it was before based on that change. So C looks like a vertical stretch. That's going to be number 33 for y equals 2 times f of x. It's C. I'll just say vertical stretch factor of 2. It's making a lot of sense. And 34 must be not, you can talk about vertical compressions, but it's going to be really hard to refer to it like that. It's not truly a vertical compression. That's kind of an icky way to talk about it. These are a little bit different, but it is a horizontal shrink. So number 34, let's see if this matches with this one. Sure enough, it does. And if there's one indication of that than anything else, it is on the x-axis. Before we had to take the log of 1 to get 0, but now we got to take the log of 1/2 to get 0. Because, well, whatever the thing is, because 1/2 times 2 is 1, and that's what gets you the log. Sorry, not the log of 1/2. You have to plug in half the value of x to take the log of 1, so you get 0 back out. So this makes a lot more sense for this one to be a vertical compression based off of that. So for f of 2x, I want to describe the way that I was stating that one. You have to take half your x value to take log of 1 to get log of 1 equals 0. My starting point is all based off of where I can take the log of 1. And if x was 1 before or 1 away from there, it works. Now I got to go half the distance because I'm about to double that. 2 times 1/2 is 1 and log of 1 is 0 that way. All right, that should be B. Okay, let's move forward. Numbers 35 to 38, write a rule. So we're not drawing graphs, we're just coming up with the rule on these ones. And I think that's true for 39 to 42 as well. Only these are exponentials, and then after that we have logarithms. So f of x equals 5 to the x power. We are going to translate 2 units down, followed by a reflection in the y-axis. So for that one, let's start with an interim function. Let's call it actually h of x. We're going to get to g of x. H of x, we take our f of x and we go 2 units down like this. So this is going to be 5 to the x power minus 2. Our g of x from here will take our h of x and reflect across the y-axis. That means we make our x negative. So here we're going to get 5 to the negative x power minus 2. Here's an answer. Another answer, which I'm totally good with, is call that 1/5 to the x power, positive x power minus 2. That one also works like that. Negative exponents reflect across the y-axis, but it also means instead of growth, we have decay for our graph. All right, number 36, f of x equals 2/3 to the x power. We're going to reflect in the x-axis, followed by vertical stretch by a factor of 6, and then a translation 4 units left. I feel like I can do all of these in the same step if you want to give it a shot. This g of x, the reflection x-axis is making the outside negative, and vertical stretch factor by 6 means negative 6. So we got to do negative 6 times this here, followed by left 4 on x, that's f of x plus 4. So the x gets replaced by x plus 4, and that's what that one's going to look like there. So no one thing had to go before the other when it comes to order. Nothing affected it. That one looks good on that. Number 37, f of x equals e to the x. We are going to horizontal shrink, horizontal compression by a factor of 1/2, followed by a translation 5 units up. Up 5, up 5. Once again, these two won't affect each other in any sort of way. A horizontal compression by a factor of 1/2 means you actually have to double your x's because x are going to be half of what they were before. And then the plus 5 comes outside of here. There's the up 5 followed by like that. Number 38, f of x equals e to the negative x power. Let's take that and let's translate 4 units right. 1 down. Followed by a vertical shrink by a factor of 1/3. Vertical compression by a factor of 1/3. All right, once again, this time I think we have to go in different order because we're going to compress the down 1 as well, unless you are really good at writing these all at one point in through distribution, which is possible. Like I have in my head what I would do. But in this one here, we have e to the... Now, if you want to go right 4, this is interesting because keep in mind... Oh, hold on. I'm not going to write e first. I want to make sure you totally get this part. I'll go the right 4 and down 1 at the same time. But this is right 4 is x minus 4, but that's just going to replace x. Not negative x, but it's going to replace x. And then the down 1 is on the outside here. So this is going to be e to the negative, and x minus 4 is inside like that in factored form. The minus 1 is still outside there. And if you'd like to simplify that, that would say e to the negative x plus 4 like that, minus 1. Your call, but that's what you can do. Now, in terms of graphing, I'd prefer this factored out. But in terms of simplifying, I guess we need that. G of x is now going to be vertically compressed by a factor of 1/3. So g of x, we got to take 1/3 of h of x. That means even the negative 1 gets thirded. So we're going to do 1/3 times e to the negative x plus 4 minus 1. So when distributed, that's going to look like 1/3 times e to the negative x plus 4 and minus 1/3. Ugly. I don't want to graph it, especially with e. No. I do a lot of copying and pasting from something like that. But that should be our equation. All right, numbers 39 to 42. Write a rule for g that represents the indicated transformation of the graph of f. No real change on these. It's just logarithms instead. It's just logarithms. We're just taking our function and doing what we're doing. So there isn't actually a change. This function can be whatever we want and we're good. Simplification may change what we do. Like for polynomials, we did a lot of like expanding our binomials and stuff. This is a vertical stretch by a factor of 6, followed by a translation 5 units down. So we can do these both in one step if we'd like to. Vertical stretch by a factor of 6 is 6 times your function. So that, and outside of the function, we'll go 5 down like this. So that should be the final result there. Number 40. Reflection in the x-axis followed by a translation 9 units left. Once again, I believe we can do these both in one step. So f of x equals log base 5 of x. Reflect x-axis, and then left 9. So that left 9 is inside the function. Reflect x-axis is making your y's negative, so we'll do negative log base 5 of, and left 9 means 9 inside of here, plus 9 opposite of, because x's have to be 9 less than what they were before. The domain is x is greater than negative 9 now on that. Number 41. Log base 1/2 of x. We're going to translate 3 units left, 2 units up, followed by a reflection in the y-axis. This is where we probably have to do these in more than one step to not mess anything up. Okay, so h of x, our interim, let's go left 3 and up 2. So left 3, up 2 will look like log base 1/2 of x plus 3 plus 2. All good there. Now our g of x is going to be the opposite, h of negative x. So now we have to put negative x in its place. I suppose you're fine there. You just got to know when you are doing something factored versus not. But this is going to be g of x is log base 1/2 of, see, would have this been negative x plus 3, or would have the negative been factored out of there, like that kind of thing. And that's the part that gets a little tricky. So it just depends on how you write that. Some people might even write 3 minus x, right? I can think of the function, if the original problem was there, they might say log base 1/2 of, and then they might put 3 minus x. Keep it at a standard form just to get a first term positive. One or the other looks pretty good. Now, notice when we go reflection in the x-axis. Now, I didn't write this, but on the inside of that function, I could factor out a negative and that would say x minus 3. Suddenly, this graph, guys, it goes 3 to the right instead of 3 to the left. But that makes sense because it said go 3 to the left and then reflect across the y-axis. That means it turns into going 3 to the right. So it makes sense that that graph is doing what it's doing there. All right, number 42. This says natural log. That doesn't say in x. It says natural log of x. We haven't graphed any natural logs. I don't know if we're going to. But f of x equals the natural log of x. We are going to translate this thing right 3, 1 up, and horizontal stretch by a factor of 8. If you follow what we did before, we can probably do this in one step. This is the natural log of right 3. We're going to go x minus 3. Oh, hold on. I want to leave some space here. We're going to go x minus 3. 1 up will be a plus 1 from there. And it says horizontal stretch by a factor of 8. That makes this a 1/8 right here. Do I stick a 1/8 there without the parentheses? Yes, because think about if you factored a 1/8 out of there, it would say x minus 24. 1/8 of 24 is 3, so it makes sense there's that. And now we're going 24 units to the right instead of 3 units to the right because we started by going 3 to the right, followed by a stretch by a factor of 8. That means it does go 8 times bigger like that, so this does work as a final. There you have it, folks. Okay, numbers 43 and 44 justify each step in writing a rule for G that represents the indicated transformations of the graph of f. I'm just going to copy and paste all of that for myself. For myselfishly. All right. H of x equals negative the opposite of f of x. Given whatever's here, reflection in the x-axis, that's what we start with. Reflect x-axis. After that, it's a substitution of your function. You sub f of x. You sub log base 7 of x for f of x. And then h of x minus 6, that's the translation. This is a weird question. Translate down 6, and then you sub your h of x function. H of x was negative log base 7 of x. Now it's sub in h of x. All right, I guess that's all we're doing on that one. Let's do it one more time on number 44. We have an exponential function. We're going to vertically stretch by a factor of 4, followed by a translation 1 unit up and 3 units left. It looks like we do those both in one step there. So let's see this one. This is the story of an exponential function who had a vertical stretch by a factor of 4. And while it went 1 up and 3 units left, I absolutely loved it when it was G. All right, 4 times f of x, that is a vertical stretch by a factor of 4. Hope I didn't give myself a copyright strike by singing so well. And then we're substituting our function, or copyright claim. Okay, and then we have h of x plus 3 and plus 1. So we are doing the translations. That's 3 left, left 3, up 1. And then we're substituting our h of x thing in there, sub h of x. Now remember, when we're subbing h of x, we have the left 3 inside there. X plus 3 is going in for x in that function. Instead of 8 to the x power, it's 8 to the x plus 3. The plus 1 is happening after that on the outside. Okay. Let's go to number 45. 46, 47, 48. Describe the transformation of the graph represented by the graph and then give an equation of the asymptote. Okay. So we start with e to the x. F of x equals e to the x. G of x equals e to the x plus 4. Now the transformation, the plus 4 is on the outside. The graph of G is a translation 4 units up from f. Hold on. So there it begins. Now from that, we get to come up with the asymptote. This is a horizontal asymptote. I'll put HA for horizontal asymptote. This is going to be y equals 4. This is of the given equation of the asymptote. They're talking about the transformed function, because otherwise it would have been y equals 0. So there's that one. The plus 4 is giving that away. Number 46, we have originally a 3 to the x power. By the way, it doesn't matter what this base is when it comes to asymptote. It's all about k. F of x equals 3 to the x power. Same is true of logs. And g of x equals 3 to the x minus 9 power. This graph, I'm just going to kind of copy and paste this stuff. I'm getting lazy. The graph of g is a translation 9 units right. Not up, but 9 units right from f. So that minus 9 in the exponent is doing that. Now my horizontal asymptote did not go up or down at all. It's not y equals 4 anymore. It's now y equals 0. Same as it ever was. We just went 9 to the right. All right, number 47 and 48 are logarithms. We got a natural log here. That means log base e. Not going to matter for the problem. G of x equals natural log of x plus 6. It's inside the function. We're going to translate 6 units to the left of this one. Now, this doesn't have a horizontal asymptote. It has a vertical asymptote. And the vertical asymptote is based off of the domain. The domain here, we can only take log of positive numbers. So for this domain, again, x plus 6 is greater than 0, so x is greater than negative 6. So your vertical asymptote is going to be at x equals negative 6. There's no horizontal that time, but just a vertical one. And then number 48, we have log base 1/5 of x and log base 1/5 of x plus 13. But the plus 13 is outside of where implied parentheses are. As you know, I'm always going to place those parentheses there. Log base 1/5 of x and g of x, but I got to place them properly. Log base 1/5 of x plus 13. It's outside of it, which means it translates upward instead of rightward, leftward, squidward, whatever you want to say. But the vertical asymptote is not going to change. G is a translation 13 units up from f. So 13 units up from f, the x tells us to be greater than 0, so x equals 0 is going to be a vertical asymptote, just like the original f of x function. There's that one. Okay, running closer to the end, number 49, modeling with mathematics. The slope S of a beach is related to the average diameter d of the sand particles on the beach by the equation. I don't know what they're talking about. Sand particles, that's interesting. I guess the more it slopes off, well, we'll see. S equals, and that's not a 5, 0.159 plus 0.118 times the log of d. Describe the transformation of f of d equals log of d represented by s, then use the function to determine the slope of a beach for each sand type below. If I wanted to rewrite this here and have this one in front, that might help me see my a better. I have no change in h, and here's my k. All right. Now, this is, I don't know if we have to say this in context, meaning like, can I just say S is or whatever? We can say sand particles based off, well, it says a log of d, so I'll just say that. So the graph, I'm just going to say the graph of S. The graph of S is a vertical stretch compression, vertical compression by a factor of 0.118. It's less than 1, so we say compression shrink, followed by a translation 0.159 units up from f of d. I'll say f. So there's the first part. It says use the function to determine the slope of a beach for each sand type below. So we're going to substitute those in for d. Fine sand, medium sand, very coarse sand, very coarse sand. I'm going to use the graphing calculator for that. Not to graph, but I'm going to use it for, you can see where I was doing my 4/3, 4/8, 3/8. I really should just use the y equals equation for it, and I'm going to right now. That was a time suck for that problem, and I'm very sorry if you had to stick around with that. I have to turn d into x here, and plus 0.159. Okay, my back. So from here, I'm going to do table set. I'm going to ask for these things. Fine sand looks to be 0.125, and there's 0.25 and 0.5 and 1. It looks like we're doubling values. Whoops. We're doubling values, which seems to make sense with respect to things. 0.125, 0.25, 0.5, and 1. So these are the... This is S. Hold on. I'm going to copy and paste this thing over so I can look at the problem again. So we have our table of values. Okay, I got them. All right, so these are... S is the grain, the slope of the beach. It's the slope of the beach. Okay, so these are the slopes. So use the function to determine the slope of the beach for each sand type below. They are right there. So S of 0.125 equals about 0.5052 for a slope. That's a minimalistic slope. And then as it gets coarser, the slope gets higher. By the way, these are rounded values. They're approximated. 1, 2, 3, 4. 1, 2, 3. I don't know if that's exact or what's going on there. But 1, 5, 9 on that one. So yeah, the larger diameter of the sand particles, the more slopes the beach is, or the other way around. Number 50. How do you see it? The graphs of f of x equals b to the x and g of x equals 1 over b to the x are shown for b equals 2. So f of x equals 2 to the x and g of x equals 1/2 to the x. Part A, use the graph to describe the transformation of the graph of f that results in the graph of g. Well, to go from 2 to the x to 1/2 to the x, you have to raise it to the negative first power. I'm just going to write these instead of b. This is f of negative x. That's what you have to do. So if you have to raise it to the negative power, then that means you need to reflect it across the y-axis. And that's... Now, they probably want you to look at the graph to do that. F to g looks like a reflection across the y-axis. So reflect, the graph of g is a reflection in the y-axis from f. Part B, does your answer in part A change when b is between 0 and 1? Explain. I suppose that's why they're asking that. No, it doesn't change. It changes the graph, but it doesn't change the way that this thing occurs. It doesn't change the transformation. So if b was between 0 and 1, that means f would be decay, but then that would mean g was growth. F would instead be the decay, and g would become the growth. Now, the reason for that is because, I mean, that's a typed explanation. A mathematical explanation, this time I will use b. As b to the negative x equals 1 over b to the x, it's also true that 1 over b to the negative x equals b to the x. So there's no change in how that thing works. You're still raising to the negative first power to make a change on that thing, and it will still be a reflection in the axis. The y-axis. Did I say y? I did. Okay. Number 51. We're going to 56. Number 51. Making an argument. Your friend claims a single transformation of f of x equals log of x can result in a function g whose graph never intersects the graph of f. Is your friend correct? Explain your reasoning. Of course. Yes, you can, instead of doing a stretch or compression or reflection, you can translate the graph any which direction, and they will now never intersect. So just, I mean, don't go like up and then right, because then they might intersect. But you know, I mentioned this with some other graphs that looked like they were intersecting. If I have a graph f of x that's right here, And then my g of x graph, even if I do just a small translation to the right, if I translate just a little bit to the right like this, these never intersect. For one, the asymptotes are going to be different. They never intersect. You might say, well, wait, these are going to be, no. This is always going to be a little bit higher than that is, no matter what it is for those things, provided that you just did a translation change. You didn't do a vertical stretch or anything like that. I could also go just a little bit up, and this is never going to hit that one when it comes to intersecting either. Just a simple translation, any which direction will work out. Your friend is correct on this one. So your friend, my friend, whoever's friend. Number 52, thought-provoking. Is it possible to transform the graph of f of x equals e to the x to obtain the graph of g of x equals natural log of x? Explain your reasoning. You can take its inverse. I don't know if that's considered a transformation. From f of x equals e to the x to g of x equals natural log of x, you can take its inverse, which also means thereby swapping x and y. Otherwise, no real transformation in terms of other reflections. Axes reflections, stretches compressions, stretches shrinks, or translations will make the graph. But I don't know what they mean here. If they just mean reflects across the line y equals x, but yes, you may reflect across y equals x. How about that? You may reflect across y equals x. That's all good. Because it's the inverse, you can reflect across y equals x. That's not a conventional reflection that we talk about, but it is still one all the same. If that's what they meant, that's how I want to state it. Otherwise, no other kind of thing. Number 53, abstract reasoning. Determine whether the statement is always, sometimes, or never true. Explain your reasoning. Part A, a vertical translation of the graph of f of x equals log of x changes the equation of the asymptote. A vertical translation changes it, never true. This is because the asymptote is vertical. So vertically translating something that's already vertical has no change in that line. That line goes infinitely. It has a vertical asymptote. So I'm explaining the rest to you based off that. Part B, a vertical translation of the graph of f of x equals e to the x changes the equation of the asymptote. Always. It takes before the asymptote, because it has a horizontal asymptote. And if the horizontal asymptote before is at y equals whatever 0, now at y equals whatever it is based on k, y equals k, it is now changed. So that's from never to always on those, because that is a horizontal. A horizontal shrink of the graph of f of x equals log of x does not change the domain. Does not change the domain. Okay, if it said it does change the domain, I would say it's often true. It's not always. Okay, you know what? This is a sometimes. Now, I was backwards on the thinking. It says does not change the domain. I want to now say never versus always. But sometimes, because if when they say log of x, do they mean no translations? I take this back. If this already has, I was thinking if it could be translated. It depends on if it could be translated. But if it just says log of x, very straightforward, the horizontal shrink does not change the domain. It always does not change the domain. Domain is x is greater than 0, and stretching or shrinking won't change that. Shrinking won't change that. Oh, hold on a second. I wonder if that considers reflections. I don't think so. But if they said shrink by a factor of negative 1/2, I don't think they can say the negative. I think that has to be stretches. So I'm going to say always for that one. D, the graph of g of x equals a times b to the x minus h plus k power does not intersect the x-axis. That's a sometimes. Depends on k. If k is less than 0, it'll cross it. If k is less than 0 and a is greater than 0, Or if k is greater than 0 and a is less than 0, it'll intersect. Otherwise, it won't. So in the case where k is less than 0 and a is greater than 0, you're looking at horizontal asymptote below here, and then a positive will go up there. Then it'll cross like that. If it is k is greater than 0 and a is less than 0 in some sort of way, it'll also cross again like that. If k is 0, it won't cross. If k and a are the same sign, it won't cross. So those are little things to consider. Number 54, problem solving. The amount P in grams of 100 grams of plutonium-239 that remains after T years can be modeled by this. So it's losing very little over time, which is very nice. So 54, we have P equals 100 times 0.99997 to the T power. Describe the domain and range of the function. Okay, domain, based on time, it says after T years, so I guess the before, it says based on 100 grams. So the domain is not all real numbers. It could be in a context-free problem, but greater than or equal to 0. We start at time 0 when we have 100 grams. There was no plutonium before that to speak of, at least as far as what we're assuming here. The range, there's still going to be plutonium left no matter what we do. P will always be greater than 0. No change in that asymptote. We'll always have a positive amount of plutonium with that. Part B, how much plutonium is left? 239 is present after 12,000 years. Let's do P of 12,000. Let's plug that into the calculator. So we're doing 100 times 0.99997 raised to the 12,000 power, and I'm getting still 69.767 grams of plutonium-239. Part C. Describe the transformation of the function if the initial amount of plutonium-239 was 550 grams. Well, if it was 550 grams instead, but it still has the same decay, you would want to change this 100 to 550. So we'd have to go from 100 to 550, which means we have to divide this by 100. You don't want to translate it upward because it still needs to shrink to 0. 550 divided by 100 is 5.5. Therefore, you'd want to vertically stretch by a factor of 5.5. You still want it to decay at the same amount. You still want it to be able to go down to 0. So with this, you want a vertical stretch instead of anything else. You need to make it 5.5 times more rather than 450 more or something like that. Part D, does the transformation in Part C affect the domain and range of the function? Explain the reasoning. No, that's the point. No, because there was no translation. No translations occurred. That's the point of this. You don't want to translate this to make that difference. I don't know if I spelled occurred correctly. I think there's probably only one R. Occurred. Ooh, I don't know. I'm gonna scroll down. All right, number 55, critical thinking. Consider the graph of the function h of x equals e to the negative x minus 2. Describe the transformation of the graph of f of x equals e to the negative x, represented by the graph of h. Does that mean we're going from h to f or f to h? Hold on. Describe the transformation of the graph of f of x, represented by the graph of h. Sounds like h is the transformation. So on number 55, we have f of x equals e to the negative x, and h of x equals e to the negative x minus 2. I can't tell. What does that look like to you? Because normally we start off with the other one kind of being the front of it and talking about it. So we'd say f of x first, and then they say describe the transformation the other way. Now I'm a little bit backwards on it, and I don't actually know which one's which. Let's see. How do they normally say it? Let's go back. Write a rule for g that represents the transformation of f. G that represents the transformation of f. represented by the graph of h. Oh my gosh, which direction is that? You always feel like f is first anyway, so I want to say that it's f. I don't want to be wrong, because I feel like it's a later problem and they want to go backwards of what it is, so I'm actually not sure. If I had to guess, I'd say we're going from f to h. Do I want to do that? Do you want to do that? Let's do it. Let's go from f to h. Okay, so if we're going from f to h, sorry about me thinking about that. It says then describe it of the graph represented by the graph of h for g. Yeah, I think that's what we're doing. So the graph of h. Oh, hold on. If I want to do this properly, here's what I want to do. I want to turn h of x into e to the negative, and this is x plus 2, because this is negative x to begin with, and there's a plus 2 there. We're going 2 to the left, not 2 to the right. And maybe that's the trick. Maybe that's all they wanted to say. Okay, the graph of h. Sorry about that long-winded thing. H is a horizontal translation, or is a translation 2 units left, not right, of the graph of f. Okay, then describe the transformation of the graph of g of x represented by the graph of h. Justify your answers. So if g of x, let's do this in blue, g of x is e to the x, h of x is e to the negative x minus 2 still, right? We have to translate 2 left and then reflect it over, right? So you can describe this one of two ways. You can either do 2 to the left and then reflect over, or reflect over and then go 2 to the right. So the graph of h is a translation 2 units left followed by a reflection in the y-axis from g, or the graph, that is way too spaced out, or the graph of h is a reflection in the y-axis followed by a translation 2 units right from g. They said justify your answers. When it comes to my first one, as far as justification goes, I'm showing from the factorization right there. Remember, if I go 2 units left of the graph of f, that means here that h of x would be f of x plus 2. 2 units left. And f of x plus 2 is e to the negative x plus 2, which is e to the negative x minus 2 when distributed. So there's that one. This one here, if I do the top version of it, if I go 2 units left first, I'm going to say h of x equals, so 2 units left would be e to the x plus 2. 2 units left. And then followed by a reflection, that means you have to do the opposite of this, which then distributes into that. Or if I reflect first, I would say h of x equals e to the negative x, there's a reflection, and then we go 2 units right of that reflection, there's the minus 2 there, which then becomes that. So one or the other can be applied to the second one, and that's kind of my justification of that. The final question, number 56, is open-ended. It says, write a function of the form y equals a times b to the x minus h plus k, whose graph has a y-intercept of 5 and an asymptote of y equals 2. Well, there's more than one. It's open-ended. Yeah, there's more than one answer to this. This can be my specialty, all depending on what we have here. It depends on your translations. Now, the first translation we have is pretty affixed here. The asymptote of y equals 2 means we gotta go right here. Our k has to be 2 in this case. K equals 2. Now, b can be whatever we want, period, as long as it's not 1 or 0 or negative, right? So I'm just b is whatever. H and a are now dependent on each other. If you're crossing through 0, 5, you can have no translation as long as a is 3. You can have either h is 0 and a is 3. That means no translation, go 3 units up. I can make h be, say, negative 1, and then if a is 1 right there, then I'd have to, well, I guess when I say b is whatever, now b is dependent on this. So if h is negative 1, then a would be 1, and b would have to be 3 in that case. So here are some examples of this. I can either do y equals, I can make a be 3. I can be 3 times, and I can make b be whatever in this case, 2 to the x power plus 2. Now it starts here, and then I just double my distance each time. Or I can do y equals, and a can be 1 times, but b would have to be 3 to the x, and h would have to be, I said -1, so this would say a +1 here, and then +2. So check out how this graph would work. +2 is the asymptote right here. My a is 1, so I go 1 unit up when I'm 1 unit left, and then I triple my distance here each time, and then I go to 5, and that hits the y-intercept of 5. So these are options and what you can do. You can also make decay values. I can do something like y equals, a can still be 1, but now I got to go to the right if b is 1/3. I can do 1/3 to the x minus 1 plus 2. Now that I'm 1 to the right, take 1/3 and multiply by 3 when I go that way. These are different options like this. It depends on what you want to do with it. I can make b whatever it is from here, as long as it's between 0 and 1 or greater than 1. But those are just some examples of that. All right, guys, and that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. For the most part, I thought things were rather successful in what I was trying to do. I had problems taking 4/3 of numbers at some point, and then that otherwise, hopefully the graphing stuff was making a little bit of sense. They had a lot of weird problems with E, and we didn't graph any natural log ones, so we'll see where the graphing goes from here. We are going to be doing a quiz review as the next thing. After that, we have to do some log property things, solving exponential equations, and modeling with exponential and log equations as well. So guys, thank you so much. Take care. I'm going to see you in the next one.